I'm going to talk about the stability of MOF in presence of water, and I'm studying that by solid-state NMR. And so first, as a quick introduction about metal-organic frameworks, there are hybrid compounds, mixed between organic and inorganic components. And in the case of the UiO-66, the samples I will talk about today, it's made of terephthalic acid and a zirconium cluster. And the samples has microporous spores, which have a size of 6 angstrom, around 6 angstrom. And it's a very nice sample since you can use in multiple applications such as catalysis or gas storage. This sample is known to be very stable, but the behavior of this material in presence of water and gas has not been long studied at the local environment. And that will be the goal of my study. So usually the characterization of MOF can be done with X-ray diffraction, but unfortunately with this kind of method, you don't have information about the defects. You can use some neutron diffraction, but you won't have information regarding the motional details. And you can do also some adsorption of isotherms. Isotherm of adsorption, and we won't have positional or dynamic data. And if you do infrared spectroscopy, you will have information of the binding site if you study some gas that are, for example, that gas that is stuck in the pores, but you won't have information of motion. And of course, you can do some computational study, but you always have to have the experimental verifications. So in combination with all these techniques, I will show you how the solid-state NMR is really useful in this study. And we will probe at the atomic scale all the nuclei that are present in this UiO-66. And with the NMR, you can have local information regarding the inorganic cluster of the MOF, but you can also have information about the framework or the molecules that are trapped in the pores. For example, we'll talk about mobility or defects, and you can also have information of binding sites when you used some interaction between gas and MOF. So in Lille, we have 5 solid-state magnets up to 1.2 gigahertz. You can see a picture on the left. And then I will mostly show you some results at high field, but of 800 megahertz. So I've been working on metal organic frameworks since several years, and with these techniques we were able, for example, in the MIL53, which has different particularities, we were able to localize the molecules that were trapped in the pores. And also in the MIL100, with the help of the GNP, we did some structural characterizations by doing some nice aluminum carbon correlation experiments. We did also in the MIL53 the insertion of a gas which is the xenon, and we did some xenon NMR where we were able to observe the breathing effect of this MOF. But using some fun nucleus like scandium NMR, scandium 45, we did some NMR that allows us to do structural determination as well. And we also observe some influence of the water in the system of the H-cast in this through the NMR. So the sample that we're looking at today, the UiO-66, where you have the full name here. And this sample is made of zirconium, is a zirconium cluster and with terephthalic acid. So this compound is really very stable, and this stability is usually attributed to the inorganic part of the MOF. And what we wanted to study is this cluster. How does this cluster can change in presence of water or in presence of gas through a multinuclear approach? Because the thing is, this kind of sample is usually first studied by NMR using spin-half nuclei like proton and carbon-13. So we did the first study with the proton NMR, and we used the sample one. We did the synthesis following the published procedure. So here you can see the linker and the proton NMR experiment. In these experiments, what you can observe is that you can distinguish the aromatic signal, the water and the ZROH group of the MOF, but you can also look at the DMF, which is the dimethyl formaldehyde that we used as a solvent during the synthesis, and is really well known that this sample is really part of the structure, but it's difficult to localize the DMF inside the compound. So if you look at the carbon-13 NMR, what you can see is the DMF has this one signature in the carbon-13 NMR. So we can do, by doing a simple head core experiments, we can localize the DMF close to the ZROH group. What you can observe as well in this spectrum, in the proton spectrum, is that the ZROH group, it has a high chemical shift bond as compared to the calculation that has been done previously by another group. And in this high chemical shift is attributed to H-bond network. So we will look at this H-bond network with a different behavior and different samples. So in these samples, what we did is we deuterated the aromatic hydrogen by using a linker, that's a special linker. And this linker was made by mechanochemistry by the group of Daniel Laurencin in Montpellier. And in this sample, what you can observe is you drastically decrease the amount of aromatic signal. That makes sense because you're deuterated those. But what you can also observe is you still have some water and a shift of the ZROH groups. So we partially deuterated the samples, and we have like a broader water signals, but it could be because also of the because of the crystallization of the MOS that was not exactly the same as the first sample. In the sample number 5, what we've done is we used the sample number 1, but we put some more, some D2O for 48 hours at 50 degrees C in order to make some exchange with the water that is inside the MOF and the proton that is inside the MOF. What you can observe here is that you still you're decreasing the amount. You're decreasing the the H-bond network and the amount of proton, and you can definitely see that the water signal decreases in intensity and in broadening, and that is because you reduce the amount of H2O compared to D2O. However, you can observe that you don't exchange all the water that is inside, and then this water should be very stuck and part of the structure as well, and it's really difficult to remove. So what we've done after this, we did some variable temperatures of those 3 samples. And what you can observe first is that even at 330 K, you don't have a collapse between the water and the ZROH signals that was with the arrow, in the orange arrows. You cannot observe any exchange between these protons. So it was really surprising to see that. Moreover, like of course you have a reduction of the proton-proton dipolar coupling as soon as you're increasing the temperature. But if you look at in details the proton signals, you can observe that you have a broadening of this signal as compared when you're increasing the temperature, and that is due to the correlation of this motion that is comparable to the rotor period. And that prevents the refocusing of the proton-proton dipolar coupling. And that includes a broadening of the signal. So in order to reduce again the proton H-bond network, we increasing the temperature and we heated the sample at 100 degrees C for 16 hours. And we have the sample 2, 4, and 6. And what is observable here is that the reducing of the DMF the reducing of the DMF signals in all the samples and the water signals. However, you still have the ZROH that could shift as well because of the reducing of the H-bond network. So through the proton NMR, you definitely have information regarding the H-bond network of those compounds. But here, what I talked about is only the proton NMR and carbon-13 NMR. But the goal of the study is more to observe the inorganic cluster. But to look at the inorganic cluster, it's more complicated because usually you have quadrupolar nucleus. And in the case of the UiO-66, you have the zirconium-91 and the oxygen-17. So in this case, you have unfortunately a quadrupolar interaction that implies the peak broadening of your sample. And in the case of some oxygen-17, you will have a problem with the natural abundance. And in case of the zirconium-91, you have a problem with the low gamma nucleus. So all of these characteristics require adapted experiments and also high field magnets. But the thing is, can we have useful information regarding the structure and the evolution of this metallic cluster when you look at these quadrupolar nuclei? So we will see that it's possible to obtain information either by doing MAS experiments using some solid echo, for example, when you will partially average the quadrupolar interaction, or you can do some static experiments using the Voskisi PMG for ultra-wide line. That will be the case of the zirconium-91. So if we look at the zirconium-91 is not an unusual nucleus, but it can give you a lot of information. It has a spin 5½ with a natural abundance of 11.2% and a relatively low gamma nucleus. So what we will do is use high magnetic field and specific experiments for the wide lines. So in the literature in 2014, the group of Yining Wang published a paper regarding the MIL-140A samples, where they observe only one crystallographic site and with a CQ of 35 megahertz. So they used the VUS QCPMG, but it was very broad, a very broad signal. And in 2021, in NatureCom, you can see the PCN221. And in these samples, they have 4 crystallographic sites where you can see the spectrum is much more complicated and you need the calculations to understand exactly what's going on. But you have CQ that goes from 10 to 25 megahertz. So what we did is we have in the UiO-66 only 1 crystallographic site. So what we've done is we used the 18.8 Tesla, so the 800 megahertz, and we used the VUS-QCPMG experiments with proton decoupling. So we did the experiments for 24 hours at room temperature, and we didn't get any signals. So we thought that maybe the problem was the mobility of the systems, and to reduce it, we used the experiments at 140K, and in 24 hours, we had like a huge difference in the signal-to-noise ratio. So all the experiments that I will present you today regarding the Zirconium-91 was recorded at 140K. So let's start with the as prepared samples. So as you can see in blue, it's the experimental spectrum. In green, you have the adidecos, and in red will be the simulations that we did with DMFIT software. So as you can see here with the UiO-66 as prepared sample, the signal was not that easy to simulate, and we need the use of the C-check model. But with this C-check model, we found a CQ of about 22.1 experiments, and this fits well with the calculations that we've done in collaborations with Christelle Gervais in France, and yes, so it fits well with the calculations. So in the second samples, what we've done is we only changed the linker. So we use the fumarate linker that you can see here. And in this, the cluster should be the same, but we just changed the linker compared to the UiO-66. And in these samples, what you can observe is that you have a nice quadrupolar line shape, and it's really easier to fit with the 1 CQ and eta Q with DMFIT. And then we observe a CQ of about 31.2 megahertz. We also changed again the linker to have the UiO-67 NH2. So you can see that we doubled the benzene ring. So we increased the size of the linker, but the cluster the metallic cluster should be the same. And in this, we can observe as well that it's similar to the UiO-66, and you have like only a C-check model to be used, because the C-check model has to be used in order to simulate the spectrum. But the core of the study was to understand the metallic cluster with the presence of water. So what we've done, we used this setup where you put the samples in an oven, and you're increasing the temperature, and in the meantime you have like a water stream that goes into the oven. So we were under steam flow at different temperature. So for UiO-66, we left the samples for 1 week, and for the 2 others, we left the sample for only 1 day. at different temperature. So that is the samples at 80 degrees C during 1 week. And what you can observe is that the line shape started to be seen, but it's most probably a mix between a C-check model and the quadrupolar behavior. But at 100 degrees C, after 1 week, you can observe that the signals has a nice quadrupolar line shape. And we can simulate it with a CQ of about 31 megahertz. These samples and these spectra are in agreement with the proton and carbon-13 experiments, as you can observe on the left. So what you can observe is that when you're increasing the temperature, you're decreasing the amount of DMF, and you're also decreasing the amount of water from the as prepared to the 100 degrees C. So we think that by doing 80 degrees and 100 degrees C, we kind of clean the samples and we reduce the amount of water. And that is also the case for the 150 and 200 degrees C, where the samples is really, the signal is really similar to only one crystallographic site of zirconium-91. So in this, what we can see is that the CQ that we observe could be very a spy for understanding the hydration level of your sample. And then we definitely think that the UiO-66 is really stable. Sorry. This zirconium cluster is very stable, even after 1 week at 200 degrees C under steam flow. Then there is the fumarate sample. In these samples, you can see that 80 and 100 degrees C, you have a C-check, you have to do a C-check model and to simulate the spectrum. And what you can observe is that 80 and 100 degrees C, you have an amount of water that is not negligible, and that may be because of the size of the pores. And at 150 and 200 degrees C, you clean the sample. There is no water anymore. And that means you have like a nice quadrupolar line shape. So the UiO-66 is also very stable after 1 day at 100, after 1 day under steam flow at different temperature. If you look at the UiO-67 NH2, it's another story. And at 80 degrees C and 100 degrees C, it was not possible to observe a nice experiment, a nice signal to noise, even after 24 hours of recording of experiments. And the main reason is, as you can observe, you have a lot of distribution in the carbon-13 NMR. You also have like a lot of water on the proton NMR. And if you observe the BET on the right of the slide, what you can observe is the BET is really low, and that could be a reason of the low signal to noise ratio at 80 and 100 degrees C. The reason is like maybe you're destroying the access to the pores, and it's difficult to observe because of the water. So the zirconium samples, the zirconium NMR is really difficult to observe because of this water. Moreover, at 150 and 200 degrees C, according to the BET, you have access to the pores, you have back access to the pores, and then that's why we can observe some signals. Anyway, the comparison between the signal to noise of the UiO-67 NH2 and the other samples is really important, because you can see that it's very low for the UiO-67 NH2. And the reason could also be that you have a lower amount of zirconium in the samples, since the linker is bigger. We looked at the zirconium-91 in this compound, and now we wanted to observe the oxygen-17. Unfortunately, as you know, the natural abundance of the oxygen-17 is only 0.04%, and you need an oxygen-17 labeling in order to record experiments in a good amount of time. And so that's why we will show you how we did enrich in the samples. And as soon as it's a quadrupolar nucleus, you need to do to use a high magnetic field to record the sample. So in UiO-66, we should observe 3 different oxygen sites, one from the mu3OH, one from the mu3O2 minus, and one from the carboxylic sites. So in the 2013, the group of England published a paper where they found the 3 different environments. And in this study, they used 0.25 milliliter of water enriched at 41% during the synthesis. And this amount of water, even if it's a small amount, that give you a cost of 250 euros for the sample. And what we can see is that we don't when they enriched the 3 oxygen sites, and so there is no selective labeling. And what we will do is reducing the cost and do the selective labeling. And that has been done with mechanochemistry with the help of Daniel Laurencin in Montpellier in France, where they did the linker preparation through mechanochemistry, and they used only 17 microliter of water enriched at 90%. And after this linker preparation, we synthesized the MOF, and that should enriched only the carboxylic acid from the MOF. So we did 4 different samples. The 2 first are the one where we used the oxygen-17 enriched linker through mechanochemistry. And the 2 others, we used natural abundance linker just for comparison. So the C samples were used with commercial linker, and the D samples were used with natural abundance linker, but we made with the same procedure at the enriched samples. That means we use mechanochemistry and 17 microliter of water, non-enriched water, like natural abundance. First, we did the carbon-13 NMR for the 4 samples, and that you can observe that we have the 3 different carbon NMR carbon sites, carbon-13 sites, and you also observe the DMF as usual. For the oxygen-17 experiments, we did the sample A and B, not the C and D because they were not labeled. And we did the oxygen-17, and what you can observe is you have a CQ of 7.2 megahertz, and these signals is attributed to the carboxylic, to the COO groups, and with the isotropic chemical shift of 275 ppm. What we first do, and we recorded the MQMS in 51 hours, and we observe only one signal. And with the DR inept, we were able to observe the proximity of the COO and the aromatic rings of the proton, the aromatic proton. Then with these samples, what we see is that the protocol, the procedure we used worked perfectly, and we enriched only the group from the COO. We didn't enrich the mu3OH and mu3O2 minus. So we only enrich the COO, and with the high level, since we can do some 2D experiments. So we had the step number 2 of the protocol was we put some water, like 1 milliliter of water that was not labeled, close to the samples of the UiO-66. We closed the big vials and we heat it at 50 degrees C for 2 days in order to for the water to go in the samples. And we used natural abundance water for the sample A, but we used water enriched in oxygen 17 at 70% for the sample B, C, and D. So what we can observe here with the oxygen 17 spectra at natural abundance so the sample A2, what you can see is first you enrich the mu3O2 minus, and you can also see the mu3OH that has overlapped with the water signal. In these samples, in the A2 signals, what you can see is that you were able, with water that was not enriched, to label the mu3O2 minus and mu3OH. So that means that at some point, the oxygen 17 that comes from the COO moves to the other signal. So that proves an exchange between the sites from the CO to the mu3O2 minus and mu3OH. So the question that raised this sample, this experiment, is that if you have an exchange between the oxygen, that means that at some point you have some change in the structure at the local structure. So the stability at long range that you observe in the crystallographic data that doesn't on diffraction data that is not observed in the NMR. What you can also see in the B2 samples is that you have a huge amount of mu3O2 minus that definitely comes from the water that is enriched. And you observe also the same kind of behavior for the C2 and D2 samples, but you also observe the huge amount of water enriched in these samples. As a quick information, like at 324 ppm, we enriched the oxygen 17 of the GMF. We enriched in oxygen 17 the GMF. That means it's really part of the structure. And then for the third step, what we've done is we increased the temperature at 150 degrees C for 5 hours in order to remove the water that we introduced in the second step. So this step is the same for all the samples, and the goal was then to observe the relief of the water signal. So as you can see on the left, the oxygen 17 experiments is that you definitely have different behavior, the three different environments of the oxygen 17. Unfortunately, you reduce the mu3OH as well when you reduce the amount of water, but you still, for the sample A3, you still observe the mu3O2 minus. So we confirm the results that we got for the step 2. If you look at the carbon-13 NMR, it's fun to observe that you don't have any, like the amount of DMF is very low after the third step. So what I wanted to show you is, like, thanks to quadrupolar nuclei, including zirconium-91 and oxygen-17, we have a clear overview of what's going on at the local environment of this cluster, of this zirconium cluster in the UiO-66, and it's a proof of the stability, but also a proof of a lability of some bonds. That is observed by oxygen 17. So I would like to thank all the people that worked with me, like Olivier Lafont and Christophe Volcrin-Thierry-Loiseau for the NMR and the preparation of the samples. Then the students at Julian Adolphe, Florian Venel, and Renal Giovino who work with me on these projects. The engineer Julien Trebox and Bertrand Doumer. Then in Montpellier, our collaboration in Montpellier and in Paris. So Daniel Laurencin, Thomas Xavier Metro, and Jessica Spakova. And in Paris, Christelle Gervais and Caroline Melo-Drasnieks. Then I would like to thank all the foundings, and that is a picture of the group of solid-state NMR in Lille. And I would like to thank you for your attention.
Thank you very much, Frederique. It was a very nice talk. The Q&A is now open, so if you have any questions, please write it in the Q&A and we will answer them. I have a question to kick off. Could you comment on the calculations that you performed to get your simulated spectra? So which program did you use, and did you have anything specific?
I mean, I didn't do the calculations. It's my collaborator, so I'm just like not competent. So I don't want to answer the question that I'm not familiar with. Sorry.
No problem. Okay. We have a question in the chat. Wonderful talk. My question is for the 91 ZR spectrum fit using a SIGEC model. Are you fitting it to a distribution or a single site?
In single sites, but so you observe a single site with the CCheck, and then you have the distribution of the CQ, and that is relative to 22, for example, here 22.1 megahertz. I don't see the questions in the chat, but
it's if you open the Q&A.
Yeah, but I mean, I need to.
So we have another question, whether 91 ZR experiments can be done under MS conditions.
Sorry?
Whether
to be honest, I don't think so, because as you can observe here, the distribution goes from -6 ppm up to 4,000 ppm, and it's really complicated to do that with the MAS. So it has been done with static condition.
I think there's a follow-up question from the same person writing using QCPMG.
Yes, they are all using QCPMG. Sorry, where is the question? I used VUS QCPMG. Yes. So it's like the broadening, the huge broadening, and the QCPMG that gives you the spikelets.
I hope that answers the question. Otherwise, feel free to write again. Then we have another question. Thanks for the great talk. What atomic distance head core is able to observe at reasonably long contact time? Is it just a second coordination sphere, or it can be larger distances?
If you have like larger distances in reasonable contact time, you can't go to higher distances. I guess you need to be close to your second sphere. Yeah, I mean it's about a few angstrom.
Yeah, thank you. Another question: the evolution of CQ from SIGEC to quad powder patterns is quite interesting. Would you happen to be involved with collaborators that might be using molecular dynamics to examine this evolution?
Yeah, we didn't observe the evolution. I mean, we didn't study the evolution of the of this C check. But it could be interesting, yes, but we didn't.
Thank you. Then another question. You've been working with DHMQC experiment that is very similar in terms of obtained structural information with headcore. Which one do you prefer, and what are main advantages of them compared to each other?
So usually we use headcore between spin half nuclei, and we use DHMQC for quadrupolar when you're involving a quadrupolar nucleus. So headcore experiment is easier to set up, but it's between two, so proton and carbon-13. But as long as you're using like oxygen-17, I've shown some DHMQC, and so with oxygen-17 is much easier to do a DHMQC because you don't have to do the spin lock for the quadrupolar nucleus, and so the quadrupolar nucleus doesn't want to stay locked. So it's usually easier to do DHMQC.
Thank you very much. I think that covers it well. There are two questions left. So one is excellent talk. Have you explored the use of DNP in these systems for signal enhancement? Understandably, access to DNP could be limited.
I did carbon aluminium experiments in these kind of systems, but we usually need a spin half nucleus in between the between the electron and the quadrupolar nucleus. So it's easier to do for me because I do have access to high field. It's easier to do the quadrupolar nucleus directly than to use the DNP. And but we did some carbon aluminium experiments on this kind of system, but not I don't see if it's possible with zirconium or oxygen-17. Oxygen-17 is more studied, but zirconium-91 is not studied at all. I guess for the DNP, I think it's really more complicated because of the bond-lining.
Okay, and then we have a final question. Thank you, Fred, for the nice tutorial. I was curious about the characterization of the hydration level. Would there be a way to quantify it?
Say that again because I don't see it.
It is in the chat. I was curious about the characterization of the hydration level. Would there be a way to quantify it?
Quantify. I don't know. It's an interesting question. Not with zirconium. Zirconium, you can see the amount, but not qualitatively. You can see it, but maybe with the proton NMR, but not with zirconium NMR, I guess.